Welcome to ODA Summit 2023. My name is Neil Peterson and I'm the president of Open Design Alliance. 2023 marks a milestone for ODA. It's our 25-year anniversary. We've accomplished a lot during the last 25 years, but today our focus is on the future. Our mission of complete interoperability for CAD and BIM continues to be well received by industry. We had another strong year of growth with 36 new companies joining us as sustaining members in 2022. Members are deploying our technology on a wide range of platforms, but the majority of companies that joined us in recent years are deploying ODA-based solutions on the web. Web is a priority for ODA, and today you're going to see a new term used to talk about our web offerings, and that term is in-web. ODA in-web is a strategic initiative to bring the full power of the ODA platform to the web. The foundational pieces of in-web are already in place, including Visualize in-web, our professional graphics engine, and CDE SDK, formerly OpenCloud, our toolkit for integrating CAD and BIM support into any common data environment. Our plans for in-web extend far beyond common data environments. For example, in the coming years, you'll see drawings in web and constraints in web to support sophisticated DWG editing. Most in-web technologies are adaptations of our core C++ components created using the advanced and scripted toolchain to generate WebAssembly. So we can deliver in-web technologies efficiently without changing the focus of our core development. Members have been asking us for years to support Solidworks, CATIA, and other 3D formats. In April of this year, we launched a new strategic development initiative for MCAD. MCAD SDK will include open support for all major 3D CAD formats under a transparent, fixed-cost licensing model, the same that we offer for all of our products. Our MCAD team has hit the ground running, and today you'll see an early demo of our support for SolidWorks and JT files. Industry response to our new MCAD SDK has been extremely positive. If you're interested in supporting this important work, please contact me. ODA has member companies in more than 50 countries, but China has been our largest source of new members during the past 5 years. To better support our Chinese members, ODA will be opening a subsidiary in China this year. We have a great program for you today with significant advancements across the board with all of our products. Enjoy the rest of the summit.
The ODA platform is an integrated set of technologies for the rapid development of engineering applications. We provide the same code base for different operating systems, the same APIs for different programming languages, universal tools for CAD and BIM data access, visualization and publishing, and a set of ready-to-use customizable solutions for both desktop and in-web development. ODA has been developing cross-platform technologies for 25 years. We support all major platforms and we have the experience to meet your platform needs for the foreseeable future. Our core software is written in C++, and to enable the use of ODA library with other programming languages, we generate wrappers with a tool called Swig. ODA provides APIs for managed languages, including C# and Visual Basic.NET, Java and Python. Support for .NET 5 and .NET 6 configuration for C# wrappers makes them available for Windows, Linux and Mac OS operating systems. This year, we completed development of an automatic generating tool and provided a new version of the .NET wrappers. Classes, functions, variable names, and namespaces are generated according to unified rules across all SDK, making the API consistent and user-friendly. The ODA Visualize SDK is designed for efficient rendering of CAD and BIM graphical data, including 2D models, 3D models, and point clouds. Visualize provides an efficient and convenient API that significantly speeds up application development. It's a cross-platform solution available for Windows, Mac, and Linux, as well as Android and iOS mobile platforms. Visualize in Web uses the same code base that simplifies web application development. To improve the quality of ODA 3D visualization, we started working on support for ray tracing. This allows us to create sophisticated graphic effects with minimal complexity, multiple reflections, color transmitting through semi-transparent surfaces, refraction on glasses materials, and so on. At the moment, we implemented graphic material effects like reflections, transparency, texturing, bump mapping, and lighting as a CPU-based solution. The next stage is porting of implemented features to the GPU pipeline to provide a real-time ray tracing solution for all ODA toolkits and ODA-based products. This year, we continue to improve and extend the abilities of Visualize SDK. We enhanced the View's 3D clipping functionality, CPU cutting planes, and it is now available both for low-level Just G API and high-level API. We enhanced the reflection plane feature that provides realistic reflections onto planar surfaces and added the ability to use them simultaneously with ground shadows. We added support for photometric lights and the Web Lights Autodesk file format that describes a light distribution from a light source. Based on file data, we prepared special textures, which represent scanning of light intensities in all directions and use them in the renderer. We extended the selections functionality to support big data in the world coordinate system. We added new functionality to support the bitmap GLES2 device and used this device for WPF applications. ODA Publish SDK supports creation of fully customized PDF documents containing 3D model views, 2D drawings and their parts, UI controls, JavaScript scenarios, and animation. The API provides convenient methods to publish CAD and BIM data to 2D and 3D PDF, including a comprehensive API for PRC data access creation and visualization. This year, we enhanced PRC creation with full support for PRC geometry compression that allows reducing output file size by up to 6 times. Publish functionality was extended with support for geospatial data when exporting DGN files to PDF, and support for the selection set option that export particular DWG or DGN entities to PDF.
The history of ODA CAD is as long as the history of the ODA itself. ODA Drawings SDK provides support for 2 major CAD formats, DWG and DGN. Drawings SDK is not limited to format support only, but provides a number of complementary tools and features to facilitate the implementation of various tasks, with interoperability being our key mission. ODA's DWG and DGN files are 100% compatible with the DWG and DGN files from the owners of those formats. As a result, your ODA-based solution may be easily integrated into any existing or new CAD workflow. 2D CAD is an essential part of the overall CAD area. 2D drawings for area planning, fire protection systems, rules for robots in warehouses, and many other errands require and efficiently use 2D CAD. ODA Drawings SDK is not something frozen. It is an actively developed product with continuous improvements. For example, starting with this year, we support two-way conversion between AIM-text entities and RTF strings. In addition to the setContents RTF method, we implemented a contents RTF method that returns an AIM-text object as an RTF encoded string. Working with text is an important part of Drawings SDK, as text is probably the first thing that comes to mind when we think of a 2D drawing. If you have a 2D drawing, it is very likely to contain some hatches. Facilitating work with hatches is a key focal point, and we have made advancements in this area as well. For instance, we simplified hatch creation using boundary comment functionality as a base. Just to remind, the boundary comment allows you to create an entity with a closed loop from multiple entities in a specified area of a drawing. In addition to pure boundary capabilities, hatch creation has the possibility of closing a contour with gaps. Gap size may be managed by means of the HPGAPTOL system variable. Contour creation is not the only way that entities may interact with each other. Another complex area of entity relationships is covered by the Constraint support was first released at the end of 2022 as a beta version. This year brought us valuable and positive feedback from our membership community. Based on this feedback, we introduced improvements that may be divided into three groups: enhancements to constraints capabilities, improvements to constraints quality, improvements in constraints behavior to work more similar to AutoCAD. As a result of these efforts, end users have the API to create all types of constraints with the given entities, list and delete constraints, convert dimensions to dimensional constraints. If you develop a UI-based application, you can speed up your development using pre-created commands for constraints creation and parameter manager for dimensional constraints. To get a quick overview of the constraints capabilities, please see our example application ODA Drawings Explorer that now has a special constraints toolbar. The whole list of the constraints now includes the following items: for geometrical constraints, coincident, collinear, concentric, fixation, parallel, perpendicular, horizontal, vertical, tangent, smooth, symmetric, equal length or equal radius. And dimensional constraints: align dimensional constraint between points of entities, horizontal or vertical dimensional constraint, two-line angular dimensional constraint, three-point angular dimensional constraint, and radial or diameter dimensional constraint. Constraints may be applied not only to 2D objects, but also to 3D objects. In some cases, it is just not reasonable or not possible to split the objects to 2D and 3D. For example, this year, we extended ODA Solid Modeler with the algorithm to generate network surfaces. Network surfaces in some cases may be absolutely flat or consist of several flat sub-elements, but there is no reason to introduce 2D and 3D network surfaces. We just have network surface native support for the ODDB surface class. With the ODDB surface create network surface method, it is possible to construct a surface by two sets of curves, U curves and V curves. Conversion and optimization, as well as intersection algorithms, are also equally required for 2D and 3D areas. As an example of a conversion and optimization algorithm, we provide conversion of ODDB sub-mesh to smooth and optimized ODDB 3D solid or ODDB surface. This was introduced last year. This conversion mode to a smooth body merges some neighboring surfaces to one surface. This year, ODDB sub-mesh and ray intersection was implemented. When talking about DGN, it is also not reasonable to try to strictly separate 2D and 3D areas. And geodata is a good example here. DGN geodata includes different geographical coordinate systems, projection types, additional transformations, geomarkers, geographical auxiliary coordinate system, and tools to work with geodata. Geodata allows us to consider the environment our model is placed in. The ability to consider the communication routes, logistics, impact, and options for further development is based on the geodata. Last year, we finished implementation of DGN geodata support. Geographical data can be associated with every DGN model using the ODDG geodata info element. This element contains information about the geographical coordinate system, datum information, reference ellipsoid data, and additional transformation data. The geographic coordinate system defines the rules for projecting 3D world coordinates to geocoordinates, longitude, latitude, altitude, and vice versa. We support over 50 different geocoordinate systems used in different parts of the world. Every model can be associated with only one geographical coordinate system and have only one ODDG geodata info element in model control elements. Geomarkers ODDG KML placemark 2D or 3D allow you to link a specific world point in a drawing to a specific point in the geographic coordinate system. They are used for the most accurate positioning of the drawing on the map and have a higher priority than geodata transformations of the model. Also, we implement sample geodata support models that allow us to convert world coordinates to geographical coordinates and back, to correct entity geometry during reprojection, when one coordinate system was changed to another one. All geodata calculation and conversion models are based on the CSMAP library. We use this library for DWG geodata support, and we try to design DGN geodata interfaces, algorithms, and protocol extensions to be similar to the ones for DWG. And of course, we implemented conversion of DGN geodata to DWG geodata and back in our DGN import and DGN export libraries. While in some cases it is not reasonable to separate 2D from 3D, in other cases we observe a 2D to 3D or 3D to 2D transformation. For example, a simple 2D entity may be used for creation of solid and sheet bodies from curves or regions. The results may be used to construct complex bodies. Extrusion and revolution functionalities allow us to create bodies from curves and regions. Enhancing those functionalities was the main focus of ODE model geometry in 2023. We have been working on providing comprehensive support for these operations through the following key functions: extrude or revolve, and create extruded or revolved, solid or surface. These functions serve as fundamental building blocks for modeling. One significant improvement we have made is the addition of support for taper angle in extrusion functionality. Currently, only line segments are supported in the profile, but we have plans to expand this support to include all types of curves this year. Two more interesting improvements. The first one: now solid bodies may be created by means of revolution from open curves. In such cases, the endpoints of the curve are extended towards the rotation axis and then closed. In addition, we have incorporated support for revolution axes that lie outside of the profile plane. To continue the topic of working with ODDB 3D solids and ODDB surfaces, we should mention the slice operation implemented this year. Slice cuts a 3D entity into two parts by plane or surface. Using extrude, revolve, and slice, you can model a wide range of real-life elements, including pipes, tanks, fittings, connectors, basements, and more. Intermediate CAD workflows require not only creation of 3D from 2D. Flattened views combine tools to construct projections and sections. The core of this functionality is the ODDB section HLR helper class. It works with 3D solids, 3D surfaces, regions, sub-D meshes, and bodies, and allows us to select a section or a projection plane, set elements to construct a section or projection, create elements of a section or a projection, get visible edges, invisible edges, and section areas. The extended version of the tool is implemented as ODDB Flatten Views helper class and additionally allows us to set color, line type, line weight, transparency, and layer settings for visible edges, and invisible edges and edge settings for section areas. The extended tool has a method to copy the result of projection or section creation to the selected block. Model documentation allows creation of smart drawing views. These views are designed to automatically update whenever changes are made to the underlying 3D model. Ongoing work increases the number of supported view types, including base view, projected view, section view, detail view, and view edit commands. Our primary focus this year was on two key aspects. First, we dedicated significant efforts to refining and improving our existing functionality. Secondly, we placed considerable time on AutoCAD compatibility, aligning with our company mission of seamless interoperability. The key achievement in this regard is the implementation of section view support. Now, section views created by ODA-backed software may be opened and processed in AutoCAD without any issues. This task required us to develop and incorporate inventor support within Drawings SDK. Speaking of compatibility with AutoCAD, we can't ignore colorbox, a way to distribute specific sets of colors and their shades across multiple manufacturers, thus following the same color frame. Colorbox are provided as separate XML text ACB extension files, so they are easy to distribute with DWG files. The open XML format makes it easy to create custom colorbooks. The ODA API allows you to read custom colorbooks and colorbooks supplied by AutoCAD.
A strategic interoperability initiative for 3D CAD data includes support for all widely used open and proprietary formats. We remain committed to open standards support, and this year we continue active development of STEP support as a main open exchange format for 3D CAD data. Also, we launched a new JT format project to support product data exchange. Open standards are not displacing proprietary formats at this point. Rather, they are complementing each other, and we see growing interest from our members in ODA support for proprietary 3D CAD formats. This year, we plan to release data access and visualization support for Solidworks and Inventor data, and our long-term roadmap includes all major 3D formats. Parasolid and ASIS are de facto standards for boundary representation data in 3D CAD applications. For a long time, ODA supported only the few versions of Parasolid required for DGN support. But this year, we began work on the Solidworks and JT formats, which can use different versions of Parasolid. To fully support Solidworks and JT, we enhanced our Parasolid support to work with any version of Parasolid data. The STEP family of formats has been actively developing during recent years, and we keep ODA STEP SDK up to date with the latest changes in industry standards. This year, we added support for AP242 and Domain Model Edition 3 Express schemas, and significantly improved performance. Performance enhancements were focused on SDAI, and we greatly improved the speed of file operations, inverse attribute calculations, and entity extents filtering. In addition to these base feature optimizations, we significantly accelerated the Express interpreter and ISO-specified find instance features used in STEP format validation. The validation engine was extended to support STEP models of different application protocols. We currently support most of the Express language constructions required for complicated AP242 model processing. To enhance ODA exchange capabilities, we implemented conversion of 3D data between STEP and DWG and DGN formats. Also, we added support for the ODA Common Data Access API for properties and model trees for STEP-related formats. In April of this year, we released Open STEP Viewer, a free application for viewing and investigating STEP files. Besides the standard visualization and model access features, the Open STEP Viewer provides a set of plugins with extended functionality, such as drafting views, validation, and export to STL for 3D printing. JT is an ISO standard 3D CAD data exchange format. It can contain any combination of approximate data, faceted, boundary representation surfaces, NURBS, product and manufacturing information, PMI, and metadata, textual attributes, either exported from a native CAD system or inserted by a product data management system, or PDM. ODA JT Toolkit enables reading or unpacking and visualization of JT data. Right now, reading scene graph, level of detail shape elements, and VREPs is implemented, and we are actively working to extend the SDK functionality. This year, we started work on Solidworks interoperability. Solidworks is a proprietary 3D CAD format commonly used for mechanical and industrial components. The format stores 3D model data, PMI, and 2D drawings. Our support for Solidworks includes reading and visualization support for part, assembly, and drawing files. At the moment, we support reading of all versions of part files and visualization of 3D data. We've been developing internal support for the IDW inventor format containing 2D data for model documentation DWG functionality. And this year, we extended our 3D CAD data interoperability with support for reading inventor IPT files. The IPT format contains 3D parts represented with solid, mesh, and surface geometry. We currently support reading IPT files and visualization of 3D solid geometry.
BIM interoperability is a key part of ODA's long-term mission. Under BIM, we support IFC and a set of related open formats, Revit and Navisworks files, DWG-based architecture and civil 3D files, and various point cloud formats as part of our Scan to BIM product. ODA IFC support is based on our advanced Express engine, which includes SDI and C++ interfaces for data access. IFC SDK is widely used by major vendors and has seen a number of major improvements during the past year. New SDI features, performance optimization, Express interpreter updates, geometry visualization enhancement, and production support for auxiliary standards such as IDS, MVD, BCF, and COVIA. The IFC 4.3 format that formalizes rail and road definitions is one of the most valuable releases within the BIM industry for the last year. The latest version is fully supported by ODA IFC SDK, and we promptly make the required changes as the scheme is still in process of certification. The next extension for tunnel definition is being actively developed by Building Smart, but the early version of this scheme is already supported in IFC SDK for member review. ODA SDK provides comprehensive support for geometric representation of principal model view definitions, including coordination view and design transfer view, including the IFC 4.3 extension with alignments and special sweeps. Along with multiple enhancements, this year we added support for hatches, annotation, fill area, and curve-bounded plane. IFC SDK includes a validation engine that can check models on different aspects. The validation engine has been improved with several standardized SDI-level validations implemented as a validation of aggregate item uniqueness, reference type correctness, and array non-optional item assignment. An automatically generated IDS API together with IDS validation have also been harmonized according to the latest stable version released by Building Smart earlier this year. It implements the highest level of validation of model semantic correctness according to user-defined requirements. The updated Model Operations API allows IFC products deletion, cloning, or extraction into other models. It has allowed us not only to create so-called federated models, which are two or more merged IFC files, but also to implement a set of complicated editing operations. The latest BIM collaboration format version 3.0 was released recently by Building Smart, and now it's a part of our IFC SDK. The new version is not backward compatible with BFC 2.1, so we implemented upward conversion in our BCF library. Both versions are available for client use. COBie is the format for delivery data collected from the BIM model, and it's widely used for various analysis or working purposes. We are happy to announce a COBie API, which is a new standardized feature of IFC SDK. The API collects appropriate BIM data about buildings and actors. For end users, COBie-related data can be accessed using OpenIFC Viewer's COBie Manager plugin. We will add support for exporting into Excel or HTML files containing COBie tables later this year.
As we switch topics from IFC to Revit, we should mention that ODA BIM-AV SDK can export RVT data to an IFC file. But due to the different model structures, the resulting IFC will contain only a subset of the original Revit data. Many tasks require direct access to the Revit model data. And that is why ODA BIM-AV SDK is so heavily used in the industry today. BIM-AV provides read access to 100% of the data in a Revit model. In addition, it includes rich visualization that supports geometry, materials, visual styles, textures, and so on, greatly expanding the potential use cases where BIM-AV can be successfully utilized. Support for temporary and auxiliary element creation, such as plane and section views, annotation elements, cable tray geometry, and others, expands the set of use cases even more. Improvements to BIM-AV have been made in several directions: view control and navigation, documentation and detailing, data management and collaboration, and additionally, we should mention the improved creation capabilities. View control and navigation improvements include: first, the ability to enable/disable a section box and control its size. It is possible, for instance, to select one or multiple elements and use the extents to create a section box. Next, the ability to draw, turn on and turn off level grids in 3D. And next, the ability to create perspective views with the same settings as in Autodesk Revit. Documentation and detailing improvements include a new multi-crop view feature that allows a crop region to be split into several crop regions, for example, to allow you to cut off some part of a view. A multi-segment view feature that allows a view to be split into segments so that every segment has its own clipping plane. A ceiling plane feature that supports creation of special views with the layout of a ceiling. For data management and collaboration, we need to mention schedule creation. Currently, BeamRV supports the creation of a new schedule, including setup fields, filtering and sorting conditions, and other properties of schedule definition. We also have the ability to walk through schedule cells and export them as CSV or HTML. And finally, we continue work at creation functionality. As RVT format uses a family-based architecture, the first important feature available in BeamRV Toolkit is the ability to import a family into a model or family database. The second one is advanced family creation support with the ability to create several family templates, all forms elements and their void form, Boolean operation on form elements, opening in host elements in a family file, and dimensions and reference plane elements. One more important area of work is the support of the Autodesk Navisworks format. As it is an aggregated format, an important issue is the support of the large files. A lot of work was done to optimize memory consumption and file processing time on different stages of the file processing. For loading, we introduced partial loading, multi-threaded loading, and direct file reading without buffering for single-threaded mode. For the visualization of Navisworks files, we implemented partial viewing with the memory limit options that allows the user to set a memory consumption limit, and support for redline data in models was also implemented in BeamNV. Navisworks files are often used for time and cost estimations. To enable this functionality in BeamNV, we recently introduced Timeliner support. The Timeliner tool enables you to link a model to an external construction schedule for visual time and cost-based planning. In addition, Timeliner data may be exported in CSV in exactly the same way as Navisworks itself. As you know, our Visualize toolkit can combine models of different formats to a single scene. Now we can export such combined Visualize scenes to NWD files. So now you have a tool to create your own federated models and to save the result to NWD for further processing, or just to convert any format to NWD through Visualize.
Scan to BIM is a research initiative focused on the conversion of point cloud data from architectural, civil, and other domains to fully classified IFC and Revit models. Our efforts for Scan to BIM are focused in three primary directions. The first direction is point cloud to mesh conversion. Here, as experience has shown, in addition to the direct transformation itself, it is necessary to perform additional actions before and after the transformations. As a result of our study and experiments, we have chosen the workflow which consists of a pre-processing stage, where we remove outliers and compute normals, a main transformation stage, which uses the Poisson algorithm, and a post-processing stage where surface trimming is performed to eliminate the typical problem of the Poisson algorithm, pedestals, in the zones where there were no points. The second direction of our activity is point cloud to BREP conversion. Such conversion allows us to eliminate intermediate mesh creation and gives the ability to extract BREPs from the point cloud directly. This approach is based on plane recognition, which is performed after segmentation of the initial point cloud. Next, after recognition of the surface boundaries, we recognize floors and walls. We are able to recognize their position, direction, and thickness, as well as the floors and walls together. This part involves some assumption and may require user feedback. Finally, the recognized objects are converted to IFC, which was chosen as the final goal for the current stage of the project. The third direction is the mesh to BREP conversion. Here we have implemented a quite complex workflow which allows us to recognize canonical surfaces, planes, spheres, and cylinders. This workflow includes many tasks, like detection of sharp edges, calculation of curvatures, segmentation of the initial point cloud, spatial extraction of planar and cylindrical segments, and finally, recognition of the canonical surfaces. The work we have already done gives us the opportunity to start the next important task, creating BREPs based on the intersection of canonical surfaces.
ODA in Web provides a set of cutting-edge products and components designed to transform the way developers work with CAD and BIM projects in the browser-based environment. It empowers developers to seamlessly store, visualize, and collaborate on CAD and BIM files in Web. The InWeb platform currently consists of 3 products: Services, Visualize, and Common Data Environment, OCD for short. Services in Web is the key product that provides the basic functionality of the platform. It includes the server core, which stores, manages, and processes CAD and BIM files, and the job runner component, which handles data conversion. Visualize in Web delivers all the capabilities of ODA's professional graphic engine for web applications. It includes 2 parts: Visualize.js, a powerful web assembly library that allows developers to visualize CAD and BIM geometry data directly in the web browsers, and the WebViewer component, a web application that demonstrates fundamental scenarios that can be implemented using ODA in Web technology. CDE in Web provides the ability to integrate CAD and BIM support into any common data environment application. It includes user management functionality, support for documents workflows, and BIM collaboration formats. Members can use these products to create custom solutions that take advantages of ODA's web server, data conversion capabilities, visualization libraries, or client-side APIs. The latest features bring even more power and versatility to your CAD and BIM workflows. Enhanced performance and optimized memory consumption, updated permissions for better control and collaboration when working with viewpoints, powerful clash detection functionality, search for specific objects, step file support, IFC and step files validation, and enhanced REST API with advanced filtering and sorting capabilities, customizable highlighting, and updated WebViewer UI UX. With these latest enhancements, we continue pushing the boundaries of CAD and BIM collaboration, providing developers with a robust platform to implement their own solutions. The Common Data Environment solution plays a decisive role in the successful implementation of BIM processes. It serves as a centralized hub for all project stakeholders to collaborate, share, and manage digital information throughout the entire life cycle of a construction project. Key requirements for any CD solution include centralized data management, version control and revision management, secure access and permissions, collaboration and communication, data integration and interoperability, file and data exchange, performance and scalability, reporting and analytics. Developing a CDE for engineers involves various challenges that need to be addressed to ensure a successful implementation. ODA has been working for many years to tight cooperation with BIM vendors and experts to deliver a proven technology for such complex solution, ODA Common Data Environment SDK.
Let's look at our solution in terms of standardization, ISO 19650, and the typical stages of information management. Starting with the work in progress stage, ODA has a significant number of supported formats, and we are looking forward to strengthening our offering with MCAD files. All of these files are supported by CDE SDK, along with the following high-level features. Collaboration together with colleagues. File versioning gives the ability to review the change history for a file, ensuring that all users have access to most recent project data. Convenient backup capabilities. The shared stage usually refers to reviewing combined models, so here we can highlight the following functionalities. Our advanced 3D viewer can be embedded in any web application, and it supports merging of BIM models, cropping, hiding, filtering elements, and viewing properties. Differentiation of access rights by groups. Creation of summary or federated models. Viewing and creating marks or annotation on model elements. Working with IFC and BCF to ensure interoperability between all project participants. Checking BIM models for clashes. During the publish step, you can share full information about the project and transfer data in any convenient format. This includes viewing and working with documentation formats such as DWG, PDF, DXF, DGN, etc. For archival, it's possible to create separate secure cloud storage on your own server for archival purposes. We provide all necessary APIs for this.
That concludes our technical presentations today. I have a couple of short notes before we close our summit. First, if you need help implementing an ODA-based solution, ODA now offers consulting services. Our experts can help you to achieve optimal design and efficient integration of ODA technologies into any application, desktop, mobile, or web. More information about ODA consulting services can be found on opendesign.com. Finally, a big part of our growth and success during the past 12 years has come from Strategic Interoperability Group, or SIG projects. A SIG is a group of ODA members who come together to provide funding for the development of a new product. Our new MCAD SDK is being developed under this program, as well as our toolkits for Revit, Navisworks, Scan2BIM, and others. ODA operates these SIG projects at cost as a service to our members. It's a highly cost-effective solution for some of today's most complex interoperability problems. We have 7 SIG projects running currently, and we're open for more. Let us know if you have an interoperability challenge that might be a good fit for our SIG program. Thank you for your attention. If you have any questions about anything from today's program, don't hesitate to contact us. We will be very happy to help you.